Hi, in this video we'll be looking at how astronomers use the Doppler effect to measure the masses of stars in binary star systems. First, what's a binary star system? It's just a fancy name for two stars in orbit around one another. The same way that a planet can orbit a star, and both the planet and the star orbit around their common center of mass. You do remember that, right? Well, the same way that can happen, we can also have two stars that orbit around their common center of mass. This sounds weird because we don't live in a star system like that, but in fact it's actually very common. About 2/3 of all stars live in these so-called binary star systems. And when we have a star system like this, we can see, if we zoomed in a lot, way more than modern telescopes are capable of, we can see these two stars moving around in their orbits around that common center of mass. So the center of mass in this simulation is that X right there. X marks the spot. That's the center of mass, and then both the high mass and the low mass star move around that common center. To start out with, I've oriented the system so that the stars are moving in the plane of the screen. So they're not moving towards you or away from you, and instead they're just going in a circle. This is to get us oriented so we know what the system looks like before I start messing around with it. If we see this on the sky, it's actually impossible to measure masses in a star system like this one. Why is that? It's because the only way we can get a Doppler shift is if a star is moving towards or away from the observer. If the star is moving purely in the plane of the screen, or in the plane of the sky, if we're looking with a real telescope, we can't measure its motion using the Doppler effect. If we want to use the Doppler effect to measure stellar masses, we need to look at systems that are not like this one, but that are tilted a little bit, at least a little bit, compared to our line of sight. As the star system starts tipping so that the plane of the star's orbits starts moving more towards the observer, we can see that whole system begin to shift. I'm not changing the orbits of the stars at all. I've just changed it so that the system, instead of being viewed face on, is now tilted a little bit towards the observer. Now, if we went and looked at this star system, we would see that there is some motion towards and away from the observer. So we'd measure a Doppler shift, and we could estimate some masses for stars in this system. But there's a problem. I'm not capturing all of the motion of the stars in this star system. The same way when we were looking at the system face on, we were seeing no motion. We're still not seeing all of the motion in that second configuration that I just showed you. So the only way we're going to get all of the motion of the stars and to get a true mass is if we look at the system in a configuration that we call edge on. Otherwise, we measure what's called a minimum mass, which is how much mass there has to be if we're looking at the system edge on. If we're not, there has to be more mass present to explain the total observed motion. So astronomers can only measure a true mass if we're looking at the system like this. So the stars are moving all towards us or all away from us, at least at some point in their orbit. If that's true, then we can get the true mass of the stars in the system. And you'll notice something changed when I went from that intermediate case to the final case. And that something is what you're seeing in the upper right-hand corner of your screen. That's showing you the total light coming from these two stars as a function of time. It's been labeled phase on the x-axis. That's basically a way of saying where we are in the orbit. And you'll notice as time continues to pass, that red line comes across and then it resets and just keeps going. If we're looking at a system edge on, or nearly so, like this, or maybe like that, we see one star move in front of the other one and eclipse it a little bit. And by looking at those eclipses, we can say, aha, this star system is edge-on, or nearly so. So we can get a very good idea of how much total mass is here. And depending on the shape of those eclipses, we can tell if we're really edge-on, where we have a little bit of a flat bottom here, right there, and also up here, or if we're not truly edge-on but merely close, like, say, this, because we miss that flat bottom and we have a smooth curve. In systems like this one, we get a true mass, and we can figure out how much mass is in each star through some complicated math we're not going to talk about. These systems, though, they're really, really rare. Only a tiny, tiny fraction of all the stars in the sky point to us like this, so it's not generally possible to directly measure the mass for a star using the Doppler effect. And instead, if we want to know the mass of a particular star, for the most part, we have to use something else, like, say, luminosity and the knowledge that it's a main sequence star. And we'll talk more about that in the lecture and in the readings. Thank you for joining me. Bye for now.